Have you ever watched a log burn in a campfire until there's nothing left but a tiny pile of ash and wondered, where does all that matter actually go? Like, did it just disappear into thin air? Well, today in this explainer, we're going to act as chemical detectives to uncover a fundamental rule of the universe. We are cracking this case wide open. Here's our game plan. We've got the law of conservation of matter, reactants and products, tracking atoms in reactions, balancing chemical equations, and finally, a recap and a transfer question. Let's get to it. Section 1. The law of conservation of matter. This is the absolute golden rule of chemistry. Here's the big takeaway. Matter cannot be created or destroyed, period. Whether a substance is going through a chemical change, like an old bike rusting, or a physical change, like ice melting on a hot day, the total amount of matter stays exactly the same. The atoms don't just vanish into the void, they just rearrange themselves. It's kind of like taking apart a spaceship made of building blocks and snapping those exact same blocks back together to build a car. Now you're probably thinking, hold on, when I burn a piece of paper, it definitely gets lighter. Well, that's because things like digesting food or burning a fire happen in an open environment, and gases escape. Carbon dioxide and water vapor literally just float away. To truly observe mass being conserved, we have to trap everything in what scientists call a closed system. If we seal our reaction tightly inside a glass box, the mass of that box will remain perfectly unchanged from start to finish because nothing can escape. Moving on to Section 2, reactants and products, the before and after of a reaction. Think of every chemical reaction as a transformation. We always start with our ingredients, which we call reactants, and we place those on the left side of our equation. Through the reaction, these starting substances completely transform into brand new materials, called products, and those go right over on the right side. So reactants go in, products come out. Before we start actually tracking our atoms from left to right, we've got a couple golden accounting rules to nail down. Look really closely at how these formulas are written. A small number slightly below the letter, that's a subscript, like the 2 in H2, that means those atoms are physically bonded together into a single molecule. But a large full-size number out in front, a coefficient, like the 2 in 2H, that just tells us how many of those independent, unbonded atoms or molecules we have floating around. This distinction is absolutely crucial. Section 3, tracking atoms in reactions. We're going to use a methane combustion model for this. Let's look at a practical scenario, kind of like turning on your gas stove. On the reactant side, we've got methane gas, CH4, reacting with diatomic oxygen, O2. That arrow right in the middle means a reaction is taking place, yielding our products on the right, carbon dioxide, CO2, and water, H2O. So if we create a visual tally table to track our cosmic building blocks, we instantly see a massive problem. The math doesn't add up. Look at the carbon. 1 on the left, 1 on the right. Cool, that's fine. But we have 4 hydrogens on the left and only 2 on the right. And we have 2 oxygens on the left, but 3 on the right. This setup is literally violating the golden rule of the universe. Let's do a quick pause check. Scan our tally table really fast and tell me which specific atoms are currently breaking the law of conservation of matter. The answer is hydrogen and oxygen. We can't start with 4 hydrogen atoms and end up with just 2. Like, where did the other 2 go? And there is no way we can start with 2 oxygen atoms and miraculously end up with 3. Matter can't be created or destroyed, so we've got to fix this equation to reflect reality. Section 4, balancing chemical equations, where we actually make the math work. Time to put on our accountant hats. We follow 3 strict rules here. Step 1, write the unbalanced equation, which is done. Step 2, count the atoms on both sides using a tally table, also done. Step 3, and seriously, this is the most critical rule in all of chemistry. We add coefficients to balance the atoms, but we never change the subscripts. We can only add whole numbers to the front of molecules to change their quantity. If you mess with those tiny subscript numbers, you completely change the chemical identity. H2O is water, right? But H2O2 is hydrogen peroxide. You definitely do not want to drink hydrogen peroxide. All right, let's fix the hydrogens first. We've got 4 on the reactant side and only 2 on the product side, locked up inside that water molecule. By placing a large coefficient of 2 in front of the water product, giving us 2 total water molecules, our hydrogen atoms are perfectly balanced at 4 on both sides, because 2 times 2 equals 4. Time for our second pause check. Now that we've added that 2 in front of the water, it affects the oxygen in the water as well. So count carefully across all the products on the right side of the equation. How many total oxygen atoms are there now? Brilliantly deduced. There are exactly 4 oxygen atoms in total on the product side. We have 2 oxygen atoms sitting inside our single CO2 molecule, and we now have 2 more oxygen atoms because we have 2 whole molecules of water. 2 plus 2 is 4. But wait, this means our reactant side, which only has 2 oxygen atoms, is now coming up short. To fix this final imbalance, we just drop a coefficient of 2 in front of the reactant oxygen gas, the O2. That gives us 2 times 2, or 4 oxygen atoms on the left. And suddenly, looking at our tally table, the whole shebang is flawlessly balanced. 1 carbon to 1 carbon, 4 hydrogens to 4 hydrogens, 4 oxygens to 4 oxygens. And there it is, a completely balanced equation. We can read this just like a recipe now. 1 molecule of methane reacts with 2 molecules of oxygen gas to produce 1 molecule of carbon dioxide and 2 molecules of water. It perfectly obeys the law of conservation of matter, down to the single atom. Nothing lost, nothing gained, just beautifully rearranged. Section 5, our recap and transfer question. Let's test your knowledge. We covered some fantastic ground today, so keep these 4 key takeaways locked in your mind. 1. Matter is never created or destroyed, only rearranged. 2. Reactants on the left transform into products on the right. 3. A tally table is your best friend for making sure atom counts match. And 4. Always balance equations by changing the big coefficients out front, never the small subscripts, because changing a subscript actually changes the chemical itself. I want to leave you with this final, provocative transfer question to really test your grasp on closed systems. If you burn a 10-gram match in a totally sealed, unbreakable glass box versus burning it out in the open air of a campfire, how does the final mass of the container compare in both scenarios? Think about where those invisible gases go in an open system versus a closed one. I highly encourage you to explain your reasoning to a classmate. Thanks for exploring these incredible rules of chemistry with me today. Keep questioning the universe around you